Hi, my name is Ching, and welcome back to Data Structures in C++. In the previous lecture, we talked about recursion and its applications. In data structures, we use recursion to describe and implement trees. So today, we're going to first introduce trees and their terminologies. Then we will focus on a special type of tree where each node can have at most 2 children, which is called a binary tree. We will briefly talk about the implementation of binary trees. Then we will discuss several ways to traverse binary trees. Let's get started. There are many terminologies of trees. Most of them are quite intuitive. We will introduce them one by one. First, we will talk about the different parts of a tree. Then, we will talk about the path in a tree and use it to define other properties of a tree. Lastly, we will describe a tree recursively by using subtrees. Now let's talk about what trees are. Rooted tree data structures use nodes to store data. These are very similar to linked lists for a few reasons. First, the tree has a first node or a root. In this example, the root is the node A. Second, each of their nodes have 0 or more children. Also, every node except the root has only one parent. Let's take a closer look. In this diagram, the node I has 3 children, J, K, and L. H is the parent of I, and I is the parent of J, K, and L. If a node can have a various number of children, how do we call that number? This is called the degree. For example, the degree of node I is 3. Just like in real life, siblings are children with the same parent. So J, K, and L are siblings of each other. Just like trees in the real world, they have leaves. You can think of leaves as the end of branches. In data structures, there are also leaves on trees. We call those leaf nodes. Officially, they are nodes with the degree of 0, or intuitively, they are at the end of each branch. All the other nodes are called internal nodes. In this diagram, we have several leaf nodes at the bottom of the tree. All the rest of the nodes are internal nodes. You can always travel down from the root to any node. And more importantly, there is only one unique path. For example, from the root A to node F. Now let's formally define what a path is. A path is a sequence of nodes where each node is the parent of the next one, except the last one. Visually, it is a path that travels down from the tree. Such as the path from BE then to G. The length of this path is 2 because it contains 2 pieces, BE and EG. Because there's always a unique path from the root to any node, we define the length of this path as the depth of the node. In this tree, E has the depth of 2. L has the depth of 3. If we visualize the tree layer by layer like this, as we can see, all nodes at the same layer have the same depth. The height of a tree is just the maximum depth that you can go from the root. For a tree with only one node, the height is 0 because there is no path going to any other node. For an empty tree, the height is defined as -1. This height value has no specific meaning, but we will see later this definition is convenient in implementing AVL trees. We can also define ancestors and descendants because of the existence of a unique path. Ancestors are nodes that are higher along a path. For example, if there's a path from node A to node B, then A is an ancestor of B. Descendants are nodes that are lower along a path. In this example, B is the descendant of A. Because a path can have zero length, such as the path starts and ends at the same node. In this case, that node can be an ancestor and descendant of itself. To make it clear, we can add the word strict, which checks if B is a descendant of A, but B is not equal to A. Also, it is easy to see that the root node is an ancestor of all nodes. Let's see some examples. In the top tree, we mark the ancestors of node I as light blue. It contains node I and all the nodes along the path to the root. In the bottom tree, we mark the descendants of node B as orange. So it contains B and everything below it. If you look at all the orange nodes, it looks like a smaller tree with the root at node B. That's what we're going to talk about next. Subtrees are collections of nodes and all of its descendants. For example, this is the subtree of H. We can also find the subtree of E. The class definition of a tree is pretty simple. First, we have a variable value to store data. Second, we have a first child variable which stores the first child that the node has. Third, we have a next sibling variable which stores the sibling next to the current node. This looks like a special linked list. Let's visualize it. Here we describe this tree using the diagram. Following the class definition in the last slide, we have a value, first child, and a next sibling variable. The first child of node A is B. The next sibling of B is H. The first child of node B is C. Then the first child of C is D. Then E is the sibling of C, and E has two children, F and G. Now let's look at the other half. H has two children, I and M. I has three children starting from J with the siblings K and L. In this course, we are more interested in a specific type of trees where each node has at most two children. These are called the binary trees. Since there are at most two children, we can simply label them as left and right. The binary tree is defined recursively, in the sense that both the left subtree and the right subtree are all binary trees by themselves. Here are some examples of binary trees. Every node has at most two children. There are no other restrictions. So what if the node has exactly two children? This is called a full node. In this tree, we mark the full nodes red. If the binary tree only contains full nodes and leaf nodes, then this tree is called a full binary tree. Here's a full binary tree, where all white nodes are full nodes and all purple nodes are leaves. The class definition of a binary tree node is simpler than a general tree. First, it contains data. Then it has the left and right pointers for the two children. In linked lists, it is easy to traverse through all the nodes. But if a tree is a two-dimensional data structure, how do we traverse it? Let's focus on binary trees where we use P, L, and R to label the parent, left, and right child. We can assume we always visit the left child before the right child. The only question left is when to visit the parent. That gives us three ways to traverse the tree. First, we have the in-order traversal. That means the parent is visited after the left but before the right child. So the parent is in between. That's why it is called in order. Second, we have the post-order traversal. Post-order means that the parent will be visited after the left and right child. Last of all, we have a pre-order traversal. Pre-order means that the parent is visited before the left and right child. All of these traversals can be implemented recursively. Now let's do an exercise with this tree. First, let's look at this tree recursively. Starting from the root, that's the parent P. And its left child, L, is a subtree. Its right child, R, is a single node. Inside the subtree L, we can label them recursively. First, we will do the in-order traversal. Let's start from the root. Following the in-order traversal, we visit the L, P, and R in that order. We know P is A and R is E. Now, let's work on L recursively. Looking at this subtree, we follow the order L, P, and R. The in-order traversal of this subtree is CBD. Put it back to the original tree. Now we completed the in-order traversal. The output is CBDAE. Let's try the post-order traversal. Post-order traversal follows the order L, R, and P. We know R is E and P is A. Now we work on the left subtree recursively, following the order L, R, and P again. Now we have C, D, and B for the subtree. Fill the output CDB to the original tree. The complete traversal is CDBEA. Lastly, let's try the pre-order traversal. The pre-order traversal follows the order P, L, and R. We know P is A, R, and E. Now we work on the left subtree recursively, following the order P, L, and R again. We have B, C, and D. Fill the output to the original tree. The complete traversal is A, B, C, D, E. In summary, we introduced trees and their related terminologies. Then we focused on binary trees and its implementations. Lastly, we defined 3 different traversals of binary trees: in order, post-order, and pre-order. This concludes today's lecture. Have fun and happy coding. I'll see you next time. Bye.